Good evening, everyone. So today we will start our discussion by solving this question number 41, which came in GATE 2018 chemistry paper. So the question is the reaction of PCl3 with PHLi in 1:3 molar ratio yields X as one of the products, which on further treatment with CH3I gives Y. The reaction of Y with N-Butylene gives product Z. The products X, Y, and Z respectively are. So here we have been given one reaction sequence and we have to identify what are the different products forming in the different steps. Okay, so X, Y, and Z we have to identify. So first of all, let's write this equation, this reaction. So what they are saying is PCl3 is reacting with PHLi. So we are having PCl3 and it is reacting with PHLi. Also in the equation they have given the reaction as 1 is in 1:3 molar ratio. So it is 1:3. 1 mole of PCl3 is reacted with 3 moles of PHLi. So what it does is it will lead to the release of removal of 3 LiCl and PPH3 will form. Okay. So the first reaction, that is the reaction of PCl3 with PHLi in 1:3 molar ratio yields X as one of the products. So from this reaction, this first reaction, we will get PPH3 and LiCl, right? So this will be our X. Then later on what they are saying is which on further treatment with CH3I gives Y. So the further treatment of PPH3 with CH3I. I am writing it like this. This CH3I. Okay. We are getting Y. So from this we are getting Y. PPH3 and PPH3, there is a lone pair present on this phosphorus. Okay. So this lone pair can attack this carbon of CH3. Okay. And this will take place. So this is an SN2 reaction. Okay. So what will be the product from this? PPH3 plus charge with C3H and I minus. Okay. So Y will be this. And then later on, what they are doing, the reaction of Y with N-butyl lithium gives product Z. So this is Y. That means PPH3 plus CH3 I minus. This on reaction with N-butyl lithium. This 1, 2, 3, 4 and Li. Okay, so this Li will have a positive charge and this carbon will have negative charge. So if we write this as PPH3 and CHHH positive, then this delta minus, what this will do is this will abstract one of the proton from this CH3 moiety and will lead to give a minus charge. So PPH3 plus with CH2 minus Okay, so this will be forming. Here, this is H. So basically CH3, that is butane. One, two, three, four. Sorry, not here. It will be this till this point. Wait. So this plus butane plus LiI. This is what we will get. So this could also be written as, we'll write it here, PCH3 plus and CH2 minus. Okay. So this is nothing but elide, CH2. So here in this question, that the reaction of PCl3 with PHLi in 1:3 molar ratio yields X. So the first reaction which is taking place is reaction of PCl3 with 3 moles of PHLi, which is leading to the formation of PPH3. And this is the X. So therefore, among the given options, option number A is PPH4Cl. In B, it's PPH3, C, it's PPH3, D, it's PPH4Cl again. So we can eliminate option number A and D if we know what is X. And then which one further on? Treatment with CH3I. So here CH3I means PPH3 plus CH3 and I minus. So this can be written as, like, it is this, right? That is PPH3 CH3 and I. So among the given options B and C, this is the correct one. This is Y. So we can eliminate option number B as well. Option number C is the correct option. But also the next step, if we do, that is the addition of N-butyl lithium to this will generate an elide, PPS3CH2. So option number C is the correct option. Uh, so this was, if we know how to synthesize halides, this reaction would be very simple, because first of all PCl3 and PHLi, they are reacting, so LiCl will eliminate and we will get PPS3. And one of the best ways to synthesize halide is by the reaction of triphenyl phosphine, that is this PPS3, with alkyl halides. And with primary halides, the reaction goes the best. So for this given question, that is question number 41 from GATE 2018 paper, the answer, the correct option will be option number C. X is PPS3, Y is PPS3, CH3 whole I, and Z is PPH3 double bond CH2. That is the halide. Okay. So any question? Okay, then we can move on to the next question. So from 2018, most of the questions are covered from inorganic chemistry section. If you have any more questions, any more doubts, you can ask me. My mail ID is given here. So you can mail me in this ritu.pandal98@gmail.com. So now we will start solving inorganic chemistry questions from GATE 2017. So let's start with this question. That is question number 13. This came in GATE 2017 paper. So what is the question? The question is the new OO resonance Raman stretching frequency in centimeter inverse of the O2 coordinated to iron center in oxyhemoglobin is nearly how much? The options given are option number A 1100 centimeter inverse, Option number B, 850 centimeter inverse. Option number C, 1550 centimeter inverse. And option number D, 1950 centimeter inverse. So here they are asking when oxygen O2 is coordinated to hemoglobin, then at which region we are getting the Raman stretching frequency for that O2 which is coordinated to iron of this hemoglobin. Okay, so first of all, this is the structure of hemoglobin. Okay. So in hemoglobin, we have an iron 2 center and it is coordinated to 4 nitrogen from this porphyrin ring. Okay, so this is an porphyrin ring and these 4 nitrogens are coordinated to the iron 2 center and one more coordination is with one histidine residue from the protein chain and in deoxy, so this is the structure of deoxyhemoglobin and this one coordination site is available. So in oxyhemoglobin, this when O2 is coordinated, then this oxyhemoglobin. So when O2 is coordinated, all the other things will remain same. This iron center will be iron 3 and here this is coordinated with the 4 nitrogen from the porphyrin ring and this O2 dioxygen molecule is coordinated. So here the O2 which is coordinated is coordinated in bent fashion. We should know that. And this is an O2 minus species. Okay. So O2 minus means it is a superoxide. Okay. So earlier iron was in +2 oxidation state. Then after coordination to this dioxygen, iron is going to +3 oxidation state and this is this molecule. So Fe3O2 minus, O2 minus is superoxide and this is the table for like these are the vibrational and geometrical properties of dioxygen species. So for different O2 species, here the stretching frequencies are given and here O2 we can see that for O2 plus the stretching frequency is 1905 centimeter inverse. For O2 the stretching frequency, the Raman stretching frequency is 1580 centimeter inverse. For O2 minus it is 1097 centimeter inverse and for O2 2 minus it's 802 centimeter inverse. So in this case of that is in oxyhemoglobin case, it is Fe3 with an O2 2 minus, that is O2 minus, which is superoxide, and from the table we can see that for O2 minus species the stretching frequency comes around 1097 centimeter inverse. This 1097 centimeter inverse the stretching frequency. Okay, so among the given options, that is 1100, 850, 1550, and 1950. So 1100 is for O2 minus, 850 is for O2 2 minus, and 1580, this is for O2 and this is for O2 plus. So since in this case, in oxyhemoglobin case, the O2 molecule is present as O2 minus, that is superoxide, option number A will be the correct option for this question. That is the new oxygen-oxygen resonance Raman stretching frequency in centimeter inverse of the dioxygen coordinated to the iron center in oxyhemoglobin is nearly 1100 centimeter inverse. To know more about this topic, please refer to the lecture series on bioinorganic chemistry, which is given by Professor Debashis Rai from Department of Chemistry, Indian Institute of Technology, Kharagpur. So any doubts in this question? So this question is basically like as I said that for bioinorganic chemistry part you should know about a few metalloenzymes and like this hemoglobin, myoglobin, hemerythrin, hemocyanin, then cytochrome P450, um, this catalase. So these are, if you go through all these previous year question papers, you will find that they mostly it's the same type of metalloproteins given in the question. Okay, so if you know about those metalloenzymes and metalloproteins, you can answer the questions from bioinorganic chemistry. And in every year, there will be at least one question from bioinorganic chemistry. Okay, so if there are no doubts, we will move on to the next question. So the next question which we will be solving today is question number 39 from GATE 2017 chemistry paper. So the question is, the rates of substitution for the following reaction vary with ligand in the order. So the different ligands given in this question are CH3 minus, that is methyl minus, Cl minus, PH minus, and H minus. And the substitution reaction which has been given is, let's write it, PT, P, PT3, P, PT3, Cl, and H. Okay. And then their pyridine, that is Py, is the incoming ligand. So Py is the incoming ligand, and we are getting PT, triethylphosphine. Two triethylphosphine are coordinated to it, and then there is L and Py, L and P. Okay, so there's a ligand substitution. The ligand substitution reaction, and here this platinum complex which is given in the question. So this complex is basically a square planar complex. Okay. So here what is happening? This Cl ligand, Cl minus ligand is getting substituted by pyridine ligand. So for ligand substitution reaction in this square planar complexes, there is one effect which we all should be familiar, which we call trans effect. Okay. So what is trans effect? It is basically the labilization of ligands trans to the other. Okay. So here, okay, the different ligands which are given in the question are H minus, CH3 minus, and PH minus, and the other one is Cl minus. So all these ligands, they have different transdirecting property. Okay. So basically, this trans effect, this was first established in 1926, and this was observed on substitution reactions at platinum 2 complex only. So what he observed is that certain ligands facilitate the substitution of the ligand that is in a position trans to them. Okay, and there is a certain order in which we can arrange those different ligands in a series. Okay, so is this? There are certain ligands facilitate the substitution of the ligand substitution of the ligand that is in transposition to them, and it is possible to arrange different ligands in a series according to this ability. Okay,
Yes, ma'am.
so what we are talking about is, let's see, say we are having this as platinum. Okay, first, just wait. So in that series, based on that series only, uh, this PET3 is better than Cl for this effect, but what will happen in this case is platinum PET3 LCl PET3. Now this Cl comes towards the end in this series. Okay, so what happens will be pyridine is there. Okay, so if this L, this ligand L, if this is H, let's say it is H in this case. So what it will do is, since H is a better transdirecting group, platinum H PET3 PET3 and the Cl will leave. Okay, and Py will come here. So like this, the reaction will be like this. If H is there, and we can have this, can be H CH3 PH or Cl. So the options which are given here among this, So to answer this question, we should know that trans-directing series, that which ligand is more trans-directing. Okay, so if we look into that series, H minus is a better trans-directing group. That means, by better I mean, if H minus is present in this position, that is, in this case, we understood that Cl is getting replaced by pyridine, right? So Cl has to get replaced. So we have to see what is trans to it. So in transposition to this Cl, the CH3Cl, pH or H minus, all those things could be there. If this ligand L is a better trans-directing group, then the rate of reaction will be faster because it will easily remove, it will substitute the Cl minus faster if this L is a better trans-directing group. So
Excuse me.
in that series, H minus comes first and then CH3 minus followed by pH minus and Cl minus, that is the halides, come towards the end of this group as I already told. So because of that only, in this case, the different orders, different ways they have arranged. So the correct option here for this question, that is the rates of substitution for the following reaction vary with L in the order. H minus will be greater than CH3 minus, that will be greater than pH minus, which will be more than Cl minus. Okay.
Excuse me, madam.
So option number D is the correct option.
Hello.
Because you see, if it is Cl only, it will. So I think you understood. If still you have any problem, you can ask me now, or I I will also refer to this book, R.P. Sarkar, Volume 2. Okay, R.P.
Hello.
Sarkar, Volume 2. In that coordination, there is a chapter, coordination compounds. 2. Then go, you can look into that chapter. There you will find more about trans effect. And also, there is a full lecture series on coordination chemistry by Professor Devashish Rai from Department of Chemistry, IIT KGP. So there also he has discussed about the ligand substitution reactions in these platinum square planar complexes, and about he have discussed about this trans effect as well. Okay, so any questions from this?
Hello. 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 Am I audible, ma'am?
uh, so actually this trans effect is very important also to know whether, like, sometimes in questions they will give you the order of addition, how the ligands are added one by one, and then they will ask that which isomer is formed, whether it is trans or cis. So in that way, I can give you one example by which maybe it will be more clear, the concept of trans effect. Let's say we have this platinum complex in which platinum is coordinated to 4 ammonia. Okay, then we are adding Cl minus. Okay, so what will happen is platinum, one of the, now all are NS3, so only one among them we can substitute any of them. So we substituted one NS3 by one Cl. Okay, it is plus. Now, if we add another Cl minus, then what will happen is platinum, Cl, NH3, NH3, and Cl. So, why it is trans? See, in that that series, this NH3 comes after Cl minus. So here, when we are having this Cl and NH3 both, since Cl is a Cl is a better trans-directing group, the trans-directing group, then NH3. That's why instead of this ammonia getting replaced, the ammonia which is in trans position to Cl, that is getting substituted by another Cl minus molecule, and we get the trans isomer. Okay, and for synthesizing the cis isomer of that, what we have to do is we have to start with PT, Cl, 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 Cl. Okay, then we will substitute one ammonia, so it can go to any of the four positions, Cl, 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 and then again when we will substitute another molecule of ammonia, again as I said that Cl is a better trans-directing group than ammonia, so ammonia will be substituted here, that is platinum, NH3, NH3, Cl, and Cl. So this is the cis isomer. So this is one of the very common questions which comes in normal when we do our MSc. So trans effect is very important, and using that we can synthesize trans or cis isomer. So if you still have any doubts about trans effect, you can ask me. Okay, if not, we will move on to the next question. So the next question which we will be discussing today is this question. I think this is question number 9 from GATE 2017 paper. The question is the electronic ground state term for the chromium ion in chromium CN6 4 minus is what? So, what is the ground state term for this complex Cr Cn whole 6 and 4 minus? So, if you are attending all the classes, we have earlier also discussed about this term symbol. So here, first of all, what we have to check is what is the oxidation state of chromium here. Okay, so if we consider it as X, then X plus Cn carries a charge of -1, and there are 6 Cn ligands. So 6 into -1 is equal to the overall charge of this complex is -4. So X minus 6 is equal to -4, or X is equal to +2. So here chromium is in +2 oxidation state. And what is the electronic configuration of chromium? It is 3d5 4s1. Since chromium here is in +2 oxidation state, it is a D4 species. Okay. So now, if it is G4, and here we can see that CN, there are 6 CNs, so it is an octahedral complex. In octahedral, we know that 5 degenerate d orbitals will split into two energy sets. One is Eg and the other one is T2G, where Eg has dz square and dx square minus y square, whereas T2G has dxy, dyz, and dxz. So D4 means 1, 2, 3, and 4. So this will be the distribution of electrons if this is a CrCn6 4 minus is a high spin complex.
मैम इट्स पेयरिंग होगा.
Whereas if it is a low spin complex, then what will happen? 1, 2, 3, and 4, right? T2G and Eg. So now in this complex, this since the ligand which is coordinated to metal center is Cn, and Cn is a strong field ligand, and since it is a strong field ligand, the strong field ligand, so this this will be a low spin complex. Okay, that means the 4 electrons will be distributed in this manner. Now, how to find out term symbol? We know that this 1, 2, 3, 4. Okay, so there are 4 electrons, and we saw that in one cell, in one orbital, there are 2 paired electrons, and the other 2 are this 1, 2, 3, 4. So the ml values for these are +2, +1, 0, -1, and -2, right? Whereas ms for each electron is equal to half. Like for upspin, it's +half, and for downspin, it's -half. So here, if we see the S, that is summation of ms, it will be half plus half plus half. 3 are in upspin and 1 is in downspin. So it will be 1, right? And therefore the spin multiplicity that is equal to 2s plus 1 will be equal to 2 into 1 plus 1, which is equal to 3, right? And the L value will be +2 -2 plus 1 plus 0. So 1, right? Sorry, very sorry. +2, both are there. So +2 +2 +1 and 0. That is equal to 2 plus 2, 4 plus 1, 5. Okay. But if it would have been a high spin complex, then what will happen? There are 4 unpaired electrons. That means S will be, we also know that the S is n by 2, right? Where n is total number of unpaired electrons. So here half plus half plus half plus half, that is 4 by 2 which is equal to 2. So 2s plus 1 would have been 2 into 2, 4 plus 1, that is 5. And L would have been, for this case, 1, 2, 3. So 1, 2, 3, 4, that is plus 2 plus 1, 0 minus 1 minus 2, or 2 plus 1 plus 0 minus 1, that is equal to 2. Right? This would have been the L value. So this high spin and low spin makes a difference here. Now we know that for L is equal to 0, it is S, 1, P, 2, D, 3, F, 4, G, 5, H. So here in this case, we can see that the L value orbital number, that is 5. So it will be H, and the spin multiplicity, that is 2s plus 1. So 2s plus 1 is 3. So 3h will be the term symbol for this, for the ground state of this chromium ion in CrCn whole 6 4 minus 3h. That is option number B is the correct option. Okay. So for high spin, what will be? Well, if it would have been high spin complex, then for L is equal to 2. It's 0, 1, 2, right? That is SPD. So it would have been D5. So here in the option, you can see that the 5D also they gave as one option. Okay. So you should not get confused on those things. Whenever questions like this is given, first we have to check what is the oxidation number of that metal center, and then the ligand which is coordinated to it is a strong field ligand or a weak field ligand. Okay, and so it is a very simple question. So the answer for this question will be 3H, option number B. Any doubts in this question?
Hello? Hello?
Okay, if not, we will move on to the next question. That is question number 12 from GATE 2017 paper. So the question here is the hapticity of cycloheptatriene, that is C7H8, in molybdenum C7H8 CO whole 3 is how much? So for answering this question, first of all, what is hapticity? So hapticity is basically the number of atoms coordinated to the central metal atom of a ligand. You can say hapticity is something like this, like for we are very familiar with the cyclopentadienyl ligand. Okay, so this is cyclopentadienyl ligands, and it can coordinate either in eta 1 fashion, eta 3 fashion, eta 5 fashion. Uh, by eta 1, I mean that it will coordinate like this. Okay, that is only with one carbon center. So if that is the case, then it is in showing eta 1 hapticity. If it is eta 3, that means it is coordinating to these three carbon centers, these three carbon atoms. And if it is given like this, that means it is coordinating to all the 5 carbon. of this cyclopentadienine ligand. Okay. So similarly, for C7H8, right, it is 1, 2, 3, 4, 5, 6, 7. Okay. So C7H8 is this, right? 1, 2, 3, 4, 5, 6, 7, 8. Here, two hydrogens are present. So this is the C7H8 ligand. Now this C7H8 can also coordinate in either eta 1 fashion, eta 3, eta 5, right? And also it can coordinate in eta 6 fashion as well. So here, what he can coordinate in. So here, first of all, what we have to check is what is the complex is given. MoC7H8 and then CO3. So first of all, let's calculate the total number of electrons that is present except for this C7H8. So this question is to be solved by this 18 electron rule. As we all know by this time that if the complex is having 18 electrons, 18, then it is the most stable one. Okay. So for calculating that, what we do, the number of electrons, the number of valence electrons of the metal, valence electrons of the metal plus the number of electrons donated by the ligands. Okay. So here one more thing. If the hapticity is 1, then this ligand is donating only 1 electron to the metal. If it's 3, it's donating 3 electrons. If it's 5, it is donating 5. And same for this. So eta 1, this hapticity also indicates how many electrons are being donated from that ligand to the metal center. So here, first we will calculate. So molybdenum is basically a D4H2 system, right? That is D4H2, that is D6 system. So we are counting here the number of electrons by neutral method. That's why we will not care about the oxidation state of the metal. In neutral method, we just see what is the number of valence electrons present in that central atom. So it's a D6 system. D6 system means 6 electrons will come from the metal center. And we know that carbonyl donates 2 electrons each. And in this case, we are having 2 carbonyl. Okay. So 6 plus 3 to just 6. That is equal to 12 electrons. So, and for making this as a stable complex, we need 18 electrons. Okay. Then simple calculation, 18 minus 12 electrons should be donated by C7H8 ligand, that is 6 electrons. So here C7H8 ligand, that is this ligand, it should donate 6 electrons. That is hapticity is 6, right? So how here molybdenum is coordinated is, say we are having this thing. Okay, so it is coordinated to this thing. This is not there. Sorry. Okay, so like this, and then there are three CO3, and this is making it an 18 electron complex. So is this clear to everyone?
Yes, ma'am.
Okay. Then that's all for today's class. So we have discussed we started discussing questions from 2021 and till 2018, most of the questions have been discussed in the class obviously from inorganic chemistry part. And 2017, we have discussed these few questions. So if you have any doubt regarding this, please please mail me. Please feel free to mail me in the in this given mail ID, and I will definitely try to come up with a solution. Okay. Correct. If there are no more doubts, uh, we will close the session here. Okay. Thank you all. Hello.
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 Am I audible, ma'am?
Do you guys have any questions?
Am I audible, ma'am?
Hello, Pranay. You are not audible. Are you saying something? Uh, yeah,
Am I?
tell me. I can't hear your voice. You can write in the chat box.
Can you please explain?
Sorry, you are not audible. Could you please write it in the chat box? Am I audible?
Could you please explain the theory behind respect?
Okay, so for a few, I can say like for the ligands which are pi acceptor ligands. Okay, let's say for CO. Okay, so for if we are having and here. So if this ligand is CO, then what happens is for pi acceptor type ligands, it is explainable because back bonding will be there, right? And because of that back bonding, this bond which between this platinum and this carbonyl ligand, it will be more stronger, right? Pi back bonding means the bond between the metal center and this carbon ligand, this becomes stronger, right? And hence, since this bond will be stronger, so since d orbitals they are like this, what will happen is the bond between when this will become stronger, this bond. with Cl, it will polarize more and it will become weaker, and hence it will be easier to substitute this Cl ligand. Okay, so for pi acceptor ligands, we can explain like this. Also for strong sigma donor ligands like H minus, CH3 minus, it works in the same way. But what question I also have is one more one discrepancy which I find in this is in this series, like in this trans effect series, NS3 is like the Cl is a better transdirecting group than NS3. But what we know from this spectrochemical series is that NS3 is a uh, stronger ligand, right? NS3 is a stronger ligand than Cl. So what I think that NH3 with NH3 the bond with NH3 the bond of the metal should be stronger, and it should help in replacing the ligand which is trans to it. So that is not the case which is happening if we compare NH3 and Cl. So except for this thing, it affects trans. It explains the trans effect, that why it is on that, like why this trans effect is taking place. Okay, thank you. So, except for that, the other things are you can think it in that way. Even when we were taught, like when our professors taught us in during our MSc, they also told the same, that we can explain this thing by that way. But I don't know about that NS3 and Cl comparison. Wala case. Any other doubts?
Hello? Hello?
You are not audible, Kenya. Sorry. Okay, if not anything, then bye. Okay. Thank you all.
Hello?
Pranay, again, I think you are saying something, but you are not audible. Please type it in
Explains.
the chat box.
Next class, could you please explain the NS3? Next class, could you please explain? Okay. You are audible, ma'am. You are audible, ma'am. Thank you.
Okay, then thank you all.